Good afternoon. Welcome to the IWEX seminar on sensors. This afternoon we have two presentations from two companies that are spearheading innovation in their respective fields. My name is Justin Dunning. I'm the sales manager at Chelsea Technologies Group, but this afternoon I'm representing the Sensors for Water Interest Group, or SWIG. And SWIG is a not-for-profit organisation whose members include both large and small companies and organisations mainly placed within the water industry and environmental monitoring sectors, as well as academic organisations researching in these fields. We organise several workshops throughout the year in subjects pertinent to our members, and you can find out more information on www.swig.org.uk. Plug over. Right. We have two 15-minute presentations, which combines and a combined 15-minute question and answer session following. Our first speaker this afternoon will be Anna Whitaker, who is the European Sales Manager at Modern Water Cogent Environmental. Modern Water offer a portfolio of water technologies addressing freshwater availability and wastewater treatment. Anna will be presenting on inline low-level trace metal analysis for process and environmental control, which introduces some exciting new technology and details some case studies. I'll take it over to you, Anna.
Thank you, Justin. Can everybody hear me okay? Yeah? Great. Wave to the audience. Yeah, my name is Anna Whitaker. I am in charge of the Europe area, the European distributors for Modern Water, especially on the monitoring side. Just to give a background on the company, Justin has introduced Modern Water already. Modern Water in February last year acquired a company called Cogent. Cogent was founded 26 years ago in Australia under the name Chemtronics, and we have been manufacturing trace metals analysis equipment now. They are market leading. We've been manufacturing these now for over 25 years. Our technology is based on something called Anodic stripping voltammetry, and I will explain how that works. So, firstly, I'll just give a little brief background on why monitor, but I'll keep that brief because I think you probably know. Then I'll explain the technology, talk about detection limits and certifications, a bit on the applications and illustrating that with some case studies, and then finishing off with a summary of the benefits. So that's the outline. Trace metals, of course, low levels of metals that can be toxic depending on which metals they are and what level they are at. If they are released into local rivers and other water courses, they cause harm to the environment and to local wildlife. If they are present in drinking water, they are a human health risk. Where do they come from? Of course, discharge from industrial application, that's one of the major sources. Any industry to do with metals will produce metals wastewater. We have impact from resource exploitation like mining, shale gas fracking, which is currently going on now in Morecambe Bay, for example. And we have all the metals refining industries. And then on the drinking water side, that we could have contamination either accidental or deliberate in the form of a terrorist attack, for example. And finally, of course, a lot of areas in the world, including the southwest UK, have metals present naturally in the bedrock. Arsenic is a huge problem in Bangladesh, many areas of China, but like I said, also in southwest England. And if it's present in the bedrock, it can also be present in the groundwater and hence come into drinking water. So those are some of the sources of the metals that we have to monitor for. Explaining anodic stripping voltammetry, I had originally a nice animation that explains this, but that doesn't work on the system, so I'll explain it manually. What I'll do is I'll point with, yeah, this should be okay. It's an electrochemical method, so what we have is a test cell here. You have 3 electrodes, 1 working electrode, you have a counter electrode here, and you have a working electrode there, reference electrode here, and counter electrode here, and then a stirrer in the middle that stirs all the sample up. The blue little dots there, they represent dissolved metals, so they are positively charged metal ions in solution. What then happens is that the instrument applies a negative voltage, very negative, so down to minus 1300, for example, is common negative voltage. And that will cause the positively charged metal ions to reduce in the solution, and when they're reduced, they form metals that are deposited on the surface of the working electrode. So they sit there and wait. We hold the voltage at that negative voltage. The instrument then starts ramping up the voltage from very negative up towards positive again. And since each metal will have its own redox potential, each will leave the working electrode at a particular voltage. And we can measure exactly when that happens. And that allows the instrument to identify which metals that you have in solution, because they leave at that particular voltage. And when they leave, they create a current in the solution, and this current is measured in microamperes as a spike. And you can see the graph here. The graph is, x-axis here is the voltage as it goes from negative all the way to the positive here. And this is the current that's being measured. So at this particular voltage, cadmium leaves the working electrode, creates a current in solution that is measured in microamperes, and the current is proportional to the concentration of cadmium in solution. So that's the basis of the technology. So it's quite simple technology. It's a very rugged type of technology, so it's ideally suited to online applications, whereas an ICP-MS, for example, cannot be used online at all. It's also suited for portable instrumentations, which we also have. So that explains how it works. Our online instruments that we have two versions. They're called OVA5000 and OVA7000. The key feature of they're used for drinking water, lakes and rivers, wastewater monitoring, seawater, any type of industrial effluent water. The key feature with them is the fact that they provide continuous monitoring, that they give a real-time result. So they sit next to the stream. All the analysis is done automatically within the instrument. They are configurable to customer requirements. What I was going to say about the continuous monitoring, the alternative is a large facility. They will take all facilities, they will normally take samples once a day, send to a laboratory, or if they are a large facility, they will test them on site. Otherwise, send to a laboratory, and that will take anything from 2 days to 2 weeks to get the results if you're really unlucky. In the meantime, if you had something happening, you could have missed it. One sample a day does not show fluctuations in metal levels, but that's what this instrument will do. They're built to customer specifications. We have pre-treatment options, and I'll show you a bit more in detail on those shortly. They eliminate possible interferences. Full range of telemetry, which means that the instrument can be integrated into process control systems or monitored remotely as well. It's easy to operate, so it does not require a trained analytical chemist. The 7000 model is designed for faraway remote locations. It runs on low power, so it can be used with solar energy and wind power, for example. And finally, it has excellent correlation with standard laboratory methods like atomic absorption or ICP-MS. The sample treatment options I mentioned, this one here can be built into the cabinet. It's got UV, it's a UV treatment and acid digest. And this helps to break down hydrocarbons and other organics that are present in the sample. And if you are monitoring, say, a dirty river or anything with silt in, or at a slightly distance from the instrument, then you can use the pump and catch pot that is also provided. So detection limits, how does it compare with ICP and AA? The detection limits are these are minimum detection limits. Depending on metal, they range from 0.5 up to 10 ppb minimum detection limits. The upper limit is basically infinite, because of the instrument would just do dilutions. But for example, we have cadmium here at 0.5 ppb. We have copper at 1 ppb. We can separate out chromium-6 from total chromium, and those are both at 10 micrograms per liter. So this just gives you an idea of detection limits. Anodic stripping voltammetry is an approved method by environmental protection agencies around the world. So these are, I won't go through this list, but these are just some examples of the methods. We have US EPA methods, European standard method for cadmium and lead. We have a DIN method, for example, a German DIN method. So it's an approved technology by many EPAs in the world. Moving on to areas of application for this. Anywhere where we target this not just at one type of water industry, but the full range of water industries. So starting with enforcement will probably never be a big one in the UK, but in China, for example, which is our biggest market, the OVA and our portable PDV is the preferred method for the Chinese Environmental Protection Department. And they have hundreds of monitoring stations using OVAs across the country. On the municipal wastewater side, on the other hand, we have already companies in the UK using this, and this will increase, I believe, as well, with UCAS now looking at the time between sampling and analysis. On-site analysis like this will increase. Is used for discharge consents and works protection, and I have a case study to illustrate this. On the drinking water side, of course, like I mentioned earlier, deliberate or accidental contamination. Mining, this picture here, is a typical acid mine drainage, where you can see the coloration of iron being precipitated out. And that's a problem with all disused mines with acidic and highly metal contaminated water running out into river courses. Process control is an area where you can save huge amounts of money on saving of the additives and chemicals, treatment chemicals. Waste disposal as well. Food and beverage is a new emerging one for us as well. Many food and beverage companies, the water that they use in their process and to put into their beverages and their bottled water are taken directly from groundwater boreholes. And if you are in an area with high levels of metals in the bedrock, it's going to be in the groundwater. So that's an area that's coming as well. This is first illustration of wastewater treatment application. I illustrate this with a case with United Utilities at the facility in Fairsackilly in Liverpool. They receive domestic sewage and industrial waste from a catchment area with several metal plating companies present. And these are quite small companies that they quite frequently try to get away with releasing levels that are higher than what they're allowed to. This then gets into the water treatment works. If it's undetected, it will go through the water treatment works and come out the other side. And of course, then it's United Utilities that will get the fine, not the company that released it in the first place. So that's what they wanted to protect against. And they are saying that the levels are extremely variable, so they can have all of a sudden a spike of this when one of their companies in the catchment area has released some extra metals. So they will have a spike. If they take one sample a day, they will miss this spike. So with an OVA, which is sitting at the effluent point out from the treatment plant, this can pick this up straight away. It measures continuously, And if it does pick up high levels, it can automatically divert the flow into a holding tank or another stream that is where the discharge consent is not so low. So that it is protecting United Utilities from very high environmental fines. This is a slightly dramatic example of application in drinking water. This happened in China. It could not happen exactly like this in the UK, but for example, if we had a deliberate case of contamination, I think it could happen. In this case, the Guangzhou drinking water site took its water from the treatment plant directly from the Bay River. Upstream from the Bay River was a cadmium smelter. They had an accident and cadmium was released into the river. It went straight into the treatment plant. They didn't detect it, of course, because they were only taking a sample a day or whatever. It went straight into the drinking water system. Several thousand people were affected and were ill by this, and there were several people that died as a result of this contamination. And unusually for China, this was also reported in local or international press, and so embarrassing for them that they decided we needed to not have this happen ever again. So they bought one of our OVAs, they installed it at the inlet to the water treatment plant. It now sits there, it's been sitting there for 4 years, monitors cadmium, lead and copper continuously, and if it does detect high levels, it sends automatic warnings to the operators, and they can take action. So in China, this protects the drinking water supply for 4 million people. So yeah, slightly dramatic example, but you see the point. This would probably be my final case study, and I'll skip the other one. In process control, because this is interesting how much money you can save on process control. This is from a battery recycling plant in the UK, a secondary lead smelter. They recycle lead and cadmium, and they have an on-site treatment plant for this before they can release the water into the local river. The levels of metals fluctuate like this, but they weren't exactly sure how they fluctuated and at what frequency. So once they bought an OVA, the amount, and of course, they have to add flocculant to capture all the high levels as well. So they keep overdosing just to make sure that they don't release metals above their consent limit. They bought an OVA and were then able to monitor much more efficiently and could dose much more effectively. The money that they saved on the flocculant was paid for the instrument in 6 months. So that's a good example of quick money saving. I'll skip that one, and I don't have much time now, do I? Am I out of time?
Well, you're pretty much, yes.
Okay. Yeah, I'll summarize. So yes, this is summary slide. Treatment process control, as I just mentioned. If you can dose the amount of flocculant more accurately, there's huge financial savings to be made from online monitoring. Effluent monitoring. The OVA can be used to automatically divert flow or send automatic messages, which is a protection against environmental fines and litigations. As an example, a company in Holland was fined €1 million a few years ago for polluting the local harbour. That's serious money. In the UK, there's actually unlimited fines, and the directors can be put in jail for environmental pollution. So it's quite a serious issue. Drinking water monitoring, as I explained, remote warnings can protect drinking water for many people. You also have financial savings on staff costs, because if you normally would run an on-site lab, you don't necessarily have to have it staffed at weekends or at night. The OVA can do this monitoring for you. And I have another example of a mine that I went to visit in Bulgaria. They're going to get one of these systems, because currently they have 3 streams that run all the way through the mining area and come together at one point. They have one person, full-time employee, that his job is to go and sample from all these different little rivers in different places. They're going to get one OVA, it is going to sit at the confluence of these 3 rivers. All 3 streams can go into one instrument and they will know the results. They will still have to take a few samples, but they won't have to have one full-time person doing it. And finally, it does show a permanent results archive, both for your own process control, for your own records, and also to show regulators, for example. So that is the summary slide. And if you have any questions, these are my contact details. And yeah, questions afterwards.